Alright, so this is part 2 of the chapter 13 lecture tutorial. We left off discussing reaction orders and rate laws, and now we've got an example to go over. The question asks, determine the rate law and calculate the rate constant for the following reaction. So we do have a data set, and we need the data set in order to determine our orders. And of course, then we can also use that to determine our K value. And again, a rate law is always written in this particular format as highlighted down here. Rate equals K, which is your constant, times the concentration of just your reactants, and they will be to their powers of the order of the reaction. And how we determine the respective order of each reactant is by looking at this data set. So what I need to do is take a look at the two reactants, S208 and I minus. And you can see those are the only two values here that are in the table. We're not looking at the products at all. And in order for me to determine the reaction order with respect to S208 is to look at how the change in concentration of this reactant affects the rate. That means I need the concentration to change for S208, but I need it to be held constant for I minus, so that whatever change occurs in the S208, I can see by what value that affects the rate. And I'll know that the change in rate is directly attributed to the change in S208's concentration, not I minus, because I'm going to pick a point or 2 points in which I minus will remain constant and only S208 will be varied. And then I'll do the exact same and switch it up when I try to determine the order with respect to reactant I minus. So let's start with S208, and right off the bat I can see that these two trials, the 2 and trial 3, will actually give me a constant value of 0.017 molar for the concentration of I minus. So that's good. I know that these 2 points, trials 2 and 3, I minus remains constant. Hopefully that means S208 is varying. Yes, it is. It's 0.08 and 0.16. So now, let's take a look and see what's happening between trial 2 and 3. We go from a concentration of 0.08 to 0.16. That means the concentration is doubled. So what effect did that have on the rate? 1.1 times 10 to the minus 4 for trial 2, and it doubles to 2.2 times 10 to the minus 4. So we doubled the concentration, and that doubled the rate. A 1-to-1 ratio would mean that this is a first order reaction with respect to S208, and therefore the exponent for S208 when we write our rate constant down here will indeed be 1. Let's do the same thing here for I minus. I'm going to select a data set in which S208 remain the same, so there trials 1 and 2. The concentration of S208 is 0.08 molar, and so let's see what happens to I. I does vary, so that's good. Let's see what happens to I. In trial 1 we see 0.034, and in trial 2 we see it drop to 0.017, and that means it's halved. It's exactly 1/2 of what it was in trial 1. So we halved the concentration of I minus. What effect did that have on the rate? Initial rate was 2.2 times 10 to the minus 4, and lo and behold, it has dropped by 1/2 to 1.1 times 10 to the minus 4. So we have the concentration of I minus, and the rate also was reduced by a factor of 1/2. So again, it's a 1-to-1, or a directly proportional relationship. That means that the order of the reaction with respect to I minus is also 1, and the exponent in the rate law for I will also be 1. So if I was to rewrite the rate law down here, this is what it would be. Rate equals K, whatever the K is, we haven't determined that, but K times the concentration of S208 to the first power, because X, or its order, was first order, there's the 1, and times I, the other concentration of the reactant, also to the first power. Again, rate equals K times the reactant's concentrations, and each to their own power. And that's what we determined using that data set. Now the second part of the problem did ask us to solve for K. And so what we can easily do is, now that we have our rate law written, we can just plug in values. First and foremost, pick a data set. the data set is continuous and constant, and the proportional relationships that we've just discussed are carried throughout. So you can pick any data set of any trial and you should still attain the same answer. Again, pick any trial of data and plug it in. So let's take a look and see what's going on. Here we go. We have, let's say we pick trial number 1. We would plug in 0.08. For S208, we would plug in 0.034. For I minus, we know the exponents are each 1, so that's not nothing unusual. And then we'll pick the rate that corresponds to that and plug it in for the rate. So we know rate. We have the concentrations again from this table, and that means the only thing we're left to solve for right here is K. So plug in the given values and solve for K, and you should be good to go. Here's the trial. I used trial number 3 in this particular example. I plugged in values of K that I solved for. Value for concentration of S208, value for I as a reactant, all to the 1 power, of course, that was their order. I was given the K, because if you had solved this problem above, you would have gotten 2.3 times 10 to the negative 2, and of course it was given here in the problem. So you were given K, we plugged in K. Again, go back to your table, pick the concentrations, you've got the orders, plug everything in, and there you go. You've got the concentration. And you've got the rate constant. You've got your orders, and you can of course calculate rate according to the rate law. So again, very simple if you know how to navigate your way through this. Next thing to discuss is the characteristics of first, second, and zero order reactions. This is where you need to take an active approach. Slides 15, 19, and 20 go over these, and they're pretty much the same format of slides. They each tell you what the rate law would be for a first, zero, or second order reaction. We start off with first order. They'll tell you the rate law. They'll write the rate equations. They'll tell you what the half-life equations are. They will show you some graphs, and it's very important what you get out of the graphs, of course. And they'll also tell you what K represents, which is, of course, your slope. And again, what they will tell you there is what the units for K are. So speaking of slope, that's where we go to graph. And again, all of these will be reviewed in one of the slides. I believe it's slide 15 for first order. The same will be repeated in the same format for the second order and for zero order. Of course, what will change are the equations, the half-life equations, units for K, so on and so forth. Sometimes, of course, you'll be able to look at a data set like we did above and say, okay, well, the exponent is 1, so I know it's first order. The exponent was 2, it's second order. But sometimes you won't have a data set. You'll have actually a graph. And by looking at the shape of the graph and whether the slope is negative or positive, linear, which means a straight line, or exponential, exponential means curved, and then, of course, you look to see what is being plotted. What's on the x-axis? What's on the y-axis? Am I plotting concentration versus time? Am I plotting 1 over concentration versus time? Am I plotting the natural log of concentration versus time? You need to know what is being plotted against what. And by looking again at the positivity or negativity of the slope, whether it's linear or exponential, and again what is being plotted, you can then determine what the units of K are, meaning what the slope is, and that will help identify whether that reaction is first, second, or zero order without having to look at a data set. Alright, so make sure you're very familiar with those. There is a summary slide to help you. And then last but not least, a quick review of endo versus exothermic reactions. Again, this is from Chem 1. Exothermic, of course, is when heat is released. Think exo for exit. And endothermic is when heat is being absorbed. Think endo for entering of heat into the reaction. That means that your delta H is a negative in an exothermic reaction and a positive for an endothermic reaction, and this is what they look like when you plot them in a graphical interpretation. A and B are your reactants, C and D are your products, and you can see energy-wise you have a lower level of energy down here on this exothermic graph than what you began with, because you've actually lowered your energy or lost energy. Over here you can see in the endothermic graph that you have C and D at a higher energy level than A and B were, and so that means that you have more energy than what you started off with, and that means you must have gained energy. And again, that's what endothermic reactions do. They absorb energy. What this AB notation is, up top is what we call a transition state or a complex, and what this is a pseudo product. It's not really a reactant, it's not a product, but it's somewhere in between. So this is why we call it sort of a transition state or an activated complex. And basically, this is the midpoint in which you're somewhere between a reactant and a product, and hopefully you can go to completion of the reaction and form your product. The last thing to discuss here on this particular graph is E sub A, which is activation energy. Activation energy is the minimum amount of energy that is required for a reaction to occur. So that means if you don't meet that minimum requirement, if you don't get up until the top of this hill, there's no way to get to the other side. So this is kind of like trekking up a mountain, and if you don't have enough energy to get to the top, there's no way you can get to the other side. So activation energy is the difference between the starting point of your reaction up to where your activated complex or your transition state is. You can see here in the exothermic reaction, it has a much lower activation energy than the endothermic reaction does, and that's just by coincidence in this particular case, but that is what that represents. We do have an equation that helps us to express activation energy in terms of the rate constant, because again, the rate constant and the activation energy are related to one another, and they are actually inversely proportional to one another. So as you increase your activation energy, meaning you make it harder for the reaction to occur, you will decrease your rate constant because you'll slow things down. So again, this you can actually solve this mathematically. It's called the Arrhenius equation. A times the exponential value of, that means the exponent is negative EA over RT, and this will help you solve for activation energy or for K with respect to temperature. The R value given here, of course, is the large R, 8.314, and of course temperature must be in Kelvin based upon that. And again, you can solve for values, or you can see the relationship between K and activation energy.